All right, thank you very much. So we'll transition here from astrophysics to geophysics. I'll be talking about basically whether or not you expect planets to look like Earth with some amount of continents and some amount of ocean, or what I define here as a water world, that is a planet that has the surface completely covered in water, and so there's no exposed continent. And so this kind of ties into the talks earlier today about volatile delivered to planets, where here I'm basically just going to take a wide variety of initial water contents for planets and then calculate whether or not they should be water worlds, that is water covered. And so before I talk about the water cycle, as this advances, I'll talk about the carbon cycle, because it's kind of an analog to the water cycle, and it motivates why this is an important problem to look at. So just to briefly review, right, the main sources of carbon from the interior of Earth or any terrestrial planet with plate tectonics to the atmosphere-ocean system is basically through volcanism, either at arc volcanism, like the Cascade Range in northwest USA, or at mid-ocean ridges. And the main return mechanisms are seafloor weathering, basically hydrothermal alteration at the seafloor, which then gets subducted and returns carbon to the mantle. And then most importantly, silicate weathering. And so silicate weathering occurs when you have basically, right, rain falling. It mixes with CO2 to make carbonic acid, which then dissolves silicates on the continents. And then this creates like bicarbonates, which then flow into the ocean and then eventually lithify on the seafloor and then are subducted and returned to the mantle. And so importantly, the silicate weathering process occurs as a negative feedback, which stabilizes the climate of terrestrial planets. This is because chemical reactions on the surface of a planet will run faster if the climate of the planet is hotter, right? And so the silicate weathering feedback will stabilize your climate. If you put more CO2 in the atmosphere, silicate weathering will run faster, remove CO2 from the atmosphere into the interior of the planet, and reduce the surface temperature of the planet. And notably, it's not known whether or not seafloor weathering depends on the climate of the planet. And so if it does not, and then you have a water world where you no longer have silicate weathering, you would expect then the climate of the planet to not be stable. You would easily enter a runaway greenhouse unless you very finely tune the climate of the planet. And so just to look at a little schematic here, you can envision this just by looking at the habitable zone for water worlds versus planets with silicate weathering. Here, the red area of these cartoons is where oceans boil, where you enter a runaway greenhouse. The blue region is where greenhouse gases freeze. This is the CO2 condensation limit for the habitable zone. And then the green area is the habitable zone. Basically, the habitable zone for water worlds should be much, much smaller than for planets with silicate weathering and with plate tectonics. And so if we want to understand then whether water worlds are common, we need to understand how water is partitioned between the surface and the interior of the planet, that is the deep water cycle. And we can look at the deep water cycle. Basically, it's almost the same as the carbon cycle, but the intake process into the mantle is slightly different. And so here it's just using the same exact schematic, but replacing the subduction process for water, right? Water is produced from the interior to the atmosphere through volcanism, just like carbon is, but it's returned in a different way. Basically, water hydrates basalt through serpentinization, and then this hydrated basalt is then subducted in the mantle. But it's an open question so far in the literature exactly what regulates water cycling on terrestrial exoplanets and Earth itself. There are basically two leading ideas. One leading idea is that mantle convection regulates water cycling. That is, if you have a hotter mantle, you'll have more volcanism, and if you have a hotter mantle, you'll have reduced return of water into the mantle because the amount of water you can store in the crust is lessened. And then the other idea is the surface water budget. And so the second idea is relatively new, and I'll walk you through it quickly. And also, just to remind everybody, I'm assuming plate tectonics here, and it's not necessarily expected that all terrestrial exoplanets have plate tectonics. There may be other tectonic modes, like say stagnant lid tectonics or vertical heat pipe-like tectonics, and water cycling would work completely different on planets with these other tectonic regimes, so just keep that caveat in mind. And so, to envision how the amount of surface water affects water cycling, let's just go back to the schematic and say we have some amount of outgassing written by W up here and some amount of ingassing written by W down here, and we have some ocean depth. If we increase the ocean depth, we would expect that the ingassing increases just because we have more water on the surface available to ingas. And also, the outgassing will decrease because you have a greater load pressure on mid-ocean ridges, and so this reduces the amount of volcanism at mid-ocean ridges. And so, recently, Nick Cowan and Dorian Abbott have looked at this using a simple steady state model. So they assumed that water cycling was in steady state and wrote down very simple power laws. This is much simpler physics than the last talk. saying that the degassing and regassing rates are just power laws and the seafloor pressure, that is basically just the ocean depth. And so if you have more water on the surface that is a greater seafloor pressure, you'll have less outgassing, and if you have more water on the surface, you'll have more ingassing. And so using this, you can basically just predict how much water you need for the surface of the water to be surface of the planet to be covered in water as a function of planetary parameters. If I can get it to move. Okay. So here on the y-axis, this is how much water you have on the planet as a function of its total mass. That is the water mass fraction of the planet. Here normalized to Earth, where, as was mentioned earlier, Earth's water mass fraction is about 0.1%. And then on the x-axis is the planet mass normalized to Earth. And each of these lines shows different combinations of these parameter values. And if you're above each individual line, you're a water world. That is, the surface of the planet is totally covered in water. And if you're below the line, there's partial land coverage, and you have the silica weathering feedback, and the climate should be stable. And so you can see that whether or not a planet is the water world, depending on planet mass and water mass fraction, is extremely dependent on the assumed seafloor pressure feedbacks in the model. And so this is a natural problem. We don't know whether or not seafloor pressure alone regulates water cycling, but also we don't understand in detail what these power law dependencies should be for seafloor pressure. And then this is just one paradigm for water cycling. What about the other paradigm, temperature-dependent water cycling? And so in this case, as I mentioned earlier, the degassing rate is set by the Mantle temperature through the melt fraction. If you have more melt, you'll have more volcanism, and therefore you'll have more outgassing. And the regassing rate is set by the depth at which rocks becomes hydrated, because serpentization can only occur below a critical temperature. And so this was looked at recently in detail for exoplanets by Schaefer and Saslov, and they found here are the results from their numerical model for two different assumptions for the viscosity. One's a high viscosity of the mantle, which is relevant for the deeper mantle of Earth, and one for the low viscosity of the mantle. And here are the results for the fraction of the surface covered by water, where 1 would be a water world and 0 would be a planet without any surface water, as a function of time. And you can see that for the high viscosity case, none of their models, these lines are just for different planet masses, reaches a steady state over 10 billion years. But if one assumes a low viscosity relevant for the shallow mantle, you can see this phase of initial outgassing and then really fast regassing, and then you end with essentially no surface water available, which is in itself a problem for habitability, right? And so we have these two different paradigms which predict extremely different rates at which planets should become water worlds. And so I looked at this with Dorian Abbott in a simple non-dimensional framework. So we considered 3 different possibilities for water cycling. We considered this pressure-dependent framework that I talked about from Cowan and Abbott, a temperature-dependent model, and then we also looked at a hybrid model, basically combining the two, where the regassing rate is dependent on temperature. The reason why is because it has not been shown experimentally that regassing should be dependent on how much water is available on the surface, and so we basically just ignored that possibility. And then the degassing rate is dependent on pressure, and the reason why is because at late times, pressure-dependent degassing should have a greater influence on the degassing rate than the mantle temperature because the mantle is so cold. And so we use a simple non-dimensional framework because then we can understand the effects of various unknowns, because as you can see, there are lots of unknowns in this problem that affect the solution on water cycling. And nicely, we actually found that there's only one unknown that really matters, and that is how much water you can stuff in the mantle. All the other unknowns are only about a factor of 2, make about a factor of 2 difference in how common water worlds are. And given that we won't be able to observe too many water worlds for about 20 years, it's not such a big deal. So what happens if we just evolve our model looking at these 3 different paradigms for water cycling? So here I'm just showing the ocean depths that are predicted from the model as a function of time here in billions of years. And so the Earth-like ocean depth is shown by the dashed line. And each of these different lines is for the different models. So you can see that for the pressure-dependent model, there's essentially just a simple relaxation to a given ocean depth. And then for the temperature-dependent in the hybrid model, because the mantle temperature is hot at the start and then cools off with time, you have initial really fast outgassing and then really fast ingassing. In the hybrid model, you end up with something similar to the pressure-dependent model in terms of how much water is on the surface. But for the temperature-dependent model, you end up with very little water on the surface. And so you can see that at the ends of these integrations, I'm running these out to well past the edge of the universe. Each of these lines seems to flatten out. So it looks like a steady state. But if one looks at this in more detail, one can see that actually the temperature-dependent model is not in a steady state. So here I'm plotting the regassing and degassing fluxes from the model. So the solid line is the regassing flux, and the dashed lines are the degassing fluxes for each of the models with the same colors. And you can see that the hybrid model and the pressure-dependent model do reach a steady state where the lines balance out. But in the temperature-dependent model, the regassing at late times dominates over the degassing. And notably, this is actually currently what we think is happening on Earth. And so this temperature-dependent model is the most relevant for Earth. But it's possible that these other paradigms may be relevant as well. And so now, using these end results, these steady states, we can make predictions because our model is essentially analytic for how much water you need to become a water world, just like the Count and Abbott model did, but now for all of these different paradigms for water cycling. And so doing so, here I'm showing, this is the same plot as I showed before. If you're above the line, you're a water world for a given water mass fraction. And if you're below the line, you have partial land coverage. And this is, again, the x-axis is planet mass normalized to Earth. And I'm showing the Earth value of the water mass fraction, which is about 0.05% in the dashed line. And so I'm showing these different models. So black line is the temperature-dependent model, and you can see that you need quite a bit of water. You need to be about 1% of water by mass, even if you're a super Earth, to become a water world if the temperature-dependent paradigm and the pressure-dependent paradigm are correct. And notably, this line is essentially just regulated by how much water one can fit into the mantle. And so this basically maximum mantle water mass fraction solely determines where this line is. And so if one can stuff more water into the mantle of a super Earth with a different mineralogy, say it has a post-perovskite mantle, then this line would move upwards, and it would be even less likely that super Earths would be water worlds. But you can see that this hybrid line is actually very close to a limit where there's no water cycling at all, which is shown by the dashed dotted line. This would basically just be if all the water available was on the surface and then there was no water in the interior. And so if this hybrid model is relevant, one would expect that it's about an order of magnitude easier in terms of how much water you need as a fraction of the total planet mass for a planet to become a water world. And so this is a relatively large difference. And one would expect that in the future, we might actually be able to observationally distinguish this difference with telescopes such as LUVAR making maps of terrestrial exoplanets. And so just to hit the point home that the maximum mantle water mass fraction is the key unknown, here I'm showing how the maximum mantle water mass fraction, shown on the x-axis, changes the water mass fraction at which a planet becomes a water world. And one can see that it's essentially just a power law relationship between the two. And so this is a really key unknown for future experiments to determine how much water can you stuff into high-pressure minerals that are not like Earth minerals. And so just to note, other parameters only change the water world boundary by about a factor of 2. And so just to summarize, how water cycling depends on properties of the planet makes a pretty significant, about an order of magnitude difference as to whether or not water worlds are common in the universe. And potentially this could be resolved, of course, just by understanding better how water cycling happens on Earth, right? And so we could have more detailed modeling of regassing and degassing processes. And also experiments would be nice to show if basalt hydration does depend on the overburden pressure and whether or not this Count and Abbott prescription is actually relevant for exoplanets. But the coolest way, because this is an astrobiology conference, is to map surfaces of terrestrial exoplanets in reflected light with perhaps LUVAR, maybe in 20 years or so, and then actually count how many planets are water worlds and how many are not. And given some model for the water delivery to exoplanets, like Heiss was talking about earlier, then you can basically figure out which of these models is correct. And so we might be able to, in the very far future, use exoplanets to teach us something about Earth. And so I think that's really neat. And thank you very much.
Thanks, Tad. We have about a minute or so for questions, and then we'll move into a discussion.
So there's one other property of oceans that you didn't speak about, and I'm curious, is the salinity of the water. Does adding salt affect the thermodynamic properties enough to change any of your conclusions?
Huh, I have no idea. Yeah, I mean, It definitely doesn't affect the outgassing, but it may affect ingassing of water. Yeah, I don't understand serpentization enough. But yeah, there's been sessions on that earlier.
Yeah, I don't either, but that's great.
Yeah.
So my question is about the deep planet minerals, which is, it's been shown that bridgmanite cannot hold on to water very well at all. And even in a super Earth, you would still go through a bridgmanite phase. It may be shallow, but you would still have it. So if in this ingassing model, if your plate or whatever is ingassing has to go through a region that nominally can't hold on to water, how does that change the story?
Well, that seems to actually be, I mean, Earth goes through the same sort of transition. I didn't talk about this, but most of Earth's water is stuck at a region in the mantle called the transition zone. And so it would essentially be the same story as Earth. In terms of these models, all you need to do is just get the water into the mantle. And then how deep it goes is not really relevant because it should just be mixed on a mantle convection or an overturn timescale, which is relatively short. Depends on the planet properties, of course, but yeah, I would expect it not to change the story that much.
Well, I wonder because the depth of your transition zone and the sort of width of your transition zone should be smaller on super Earths as well. So I'd be curious to talk to you about that.
Yeah.
Okay, thanks, Tad. We'll move on to discussion. I certainly have a few questions, but so we've talked about planet composition and observations and the origins of water, and so I don't really have a discussion topic per se, but do we have more questions for the speaker, or do we see a theme popping up in terms of the formation of habitable planets and what we can actually observe? Yeah, Elizabeth.
Just a question for the last speaker. I may have missed it, but did we talk about topology and gravity?
Yeah, good question. So to calculate whether or not a planet should be a water world, we basically just assume that the maximum topography of a planet is exactly what it would be for Earth. And so we just say that the maximum topography is the Himalayas for an Earth-like planet. And then if you increase the mass of the planet, because it has a greater volume to surface area ratio, it should have a reduced topography. And so basically just have a scaling that says the maximum topography is the Himalayas times gravity to the -1, which accounts for that. And so then when we're calculating whether or not a planet is a water world, you're just saying if the ocean depth is greater than what the Himalayas would be on a super Earth, then you're a water world.
Can you repeat the question?
So he asked about erosion. I think the relevant thing is whether or not the continent would start flowing under its own weight. So it's not erosion. It's a much more serious constraint.
It's isostasy. Yeah. I had a question for Owen, which was about in regards to what Stephen asked in terms of magnetic fields. We may not think the Earth may not have had a magnetic field at the moment it had this proto-atmosphere. So how quickly would a planet need to have a magnetic field in order for that effect to even need to be taken into account?
For an Earth mass planet, you would have to be very quick. It loses its entire proto-atmosphere in maybe 10 million years. So if it took more than that for magnetic fields to form, then I wouldn't even expect that to be a
And how about
consideration.
as you go out to 5 or 6 Earth masses?
Out to that range, then you're going past tens of millions of years into that range, so maybe 50, 60 million years for some of the model parameters.
But is it ever a billion years or anything like that?
By the time you hit 7 or 8 Earth masses, then you're looking at sort of the billion-year timescales. But at that point, the XUV flux is dropping off, so then the solar wind would probably be the dominant loss process at that point instead.
And then another question I had was, how does that change with spectral type? Is just the different, if you're forming planets around a different star, that's not like
Right,
the
so
sun.
that's actually a great question. And so we were only looking at the sun-like stars to compare our model to the Rogers paper, which was looking at planets around sun-like stars, since it's difficult to measure the properties of those M-dwarf planets because they're so faint. But if you have that XUV saturation time around M-dwarf planets can be much longer than 100 million years that you see for sun-like stars, in which case I would expect to be able to erode larger mass planets, so you could maybe get that limit in radii pushed up a little bit, if indeed that XUV saturation time is lasting for billions of years for close-in planets. Though that's not something that I've modeled, so I'm not sure if that's actually how it would turn out.
Excellent, thanks. Any more questions for our speakers? Yeah, excellent. Yeah, Jake, go ahead.
Oh, and I have a quick question for you. I was wondering if you know how high up the X-ray flux is penetrating, so relative to the surface where the peak in X-ray absorption is?
So the X-ray absorption is typically within, so it's in a pressure coordinate would be at about 0.1 to maybe 10 pascals from the top of the atmosphere. So then it depends how much atmosphere you have accreted. So for a few weight percent, I'm not sure what the actual distance in, say, kilometers would be, so what we assumed in our model is that below that point, the atmosphere is in hydrostatic equilibrium, and so you can just calculate it from the hydrostatic equation with that upper pressure being at a few pascals.
I have a question for this scientist. Have you thought about and discussed with the relevant people the implications of your discovery that the Earth's primeval water was a factor of 2 or more lower in deuterium than the ocean, because if the primeval water is much poorer in deuterium, then, for instance, that means that, for instance, you got Mars. Okay, it's got 6 times the deuterium to hydrogen ratio that Earth does. Okay, so people have been saying, well, that means that it once had 6 times as much water or more than it does now, and the hydrogen went away, and the deuterium has been enriched accordingly. But if Mars's primeval water was only half as rich in deuterium as the Earth's ocean and not equal to the Earth's ocean, then it means that Mars has lost twice as much water than they think, and that means there was a lot more water on the surface of ancient Mars than people currently suppose, and also a lot more water on the ancient Earth, for that matter. In other words, that there's implications of this for lots of things. Have you had discussions with people about this?
No, I haven't. I do know that Lydia Hallis has looked at the D to H in some of the Mars meteorites and have found some that are equivalent to Earth oceans. So, I'm not sure that the D to H of Mars has been established yet. Certainly this has implications on the sources of water, because if it turns out we get down as low as the solar nebula gas, then that means we don't need an exogenous delivery at all. It could be some of the models that just say Earth got its water from the gases out of which we formed. I think this is very much like a question of what is the origin of life. The farther you dig, the more questions you come up with. And I think we're also seeing that there may be processes within the Earth that we have to take account of in terms of fractionation. Within the mantle, and I think that's why Steve is standing behind me also. So I think it's an interesting story that's now opening up some new avenues.
Before you come up to the mic, Steve, someone was in front of you in terms of
It was Mike. I know we.
Well, even before.
Oh,
a
right.
student. Right.
Oh, really? Yeah, come on up. You're first.
Well, hey, ladies first.
Thank you, guys. Hi, Amber Britt, Goddard Space Flight Center. I just had a quick question about the Water Worlds talk and being outside of that particular subject. It was really interesting, and I wanted to know why plate tectonics were being assumed for all of these water worlds. Is that a safe assumption for every water world that's terrestrial, or are we just looking at something that's more Earth-like?
The answer is because we don't know how volatile cycling would work if it wasn't plate tectonics.
There's work by Brad Foley that'll be coming out soon talking about the stagnant lid, the dynamics and volatile cycling on stagnant lid planets. So keep an eye out for that.
Yeah.
Thank you.
So I wanted to address Bob's comment about the Hallis et al. Result. It is very hard to lower D to H ratios. Of course, you can raise D to H ratios by hydrogen loss, but it's hard to lower them. So a low D to H ratio, I would argue, does demand a component of ingassing of hydrogen gas into the magma ocean. And I presented work we were doing at ASU. At LPSC, I presented this, a model that we're soon to publish, showing that we think that Earth accreted maybe over 10 oceans worth of water and then immediately stored much of it, much of the hydrogen in the core with an isotopic fractionation that went along with that. And so I think that might demand a radically different view of how water is stored. And then that would have implications for Mars as well, although I don't know what they'd be. Maybe you want to talk about Mars.
So on the question of Mars D2H, we published a paper in Science in 2015 in which we had mapped both HDO and H2O on the planet over several seasons using high-resolution infrared spectroscopy. And we were able to show that the D2H ratio in the atmosphere is in fact a very misleading number in terms of the average. If you do the analysis properly, what you find out is that near the polar cap, you see D2H enriched by a factor of 8 relative to VSMO. And this means that the North Polar Cap is in fact even more highly enriched in deuterium than the atmospheric water that you see. And so based on that, we compared that with the measurement of DOH in a very early meteorite from Mars, which was dated some years ago, just recently. And it had VSMO of about 1.3, DOH was 1.3 VSMO at 4.3 gigayears of age, very early. But in addition, Curiosity showed that at a Hesperian age, DOH near Gale Crater in the soil was actually enriched by a factor of 3. So if you look at this over time, you can estimate the amount of water that Mars actually had to lose in order to go from 1.3 VSMO to a little more than 8 in the current reservoir. And that turns out to have been an ocean the size of the Arctic on Mars, or if scaled to the Earth, it would have been the North and South Atlantic together. It was about 20% of the, covered 20% of the Earth's surface. So anyway, it was a lot of water, and the number we came up with was actually consistent with the amount that was required to form the valley channels. I think it was Vic Baker some 20 years ago, or 25 years ago, who actually worked on that problem. So there are 2 lines of evidence that suggest that this was in fact a correct amount for the amount of water that Mars lost over time. Why don't you come and use the mic?
What?
The Earth's original, if in other words, people have been comparing Mars's D to H to what we commonly see on Earth. And if the original Earth had a D to H ratio much lower than what we commonly see on Earth, that moves the baseline on these calculations so that it could be twice as much water. In other words, if you're comparing Mars's elevated D to H to, the water in the ocean here, but really should be comparing it to the primeval water here, then the elevation is twice as much.
That's true, but we really compare it with the value at 4.3 gigayears. That is the value in the Yamamoto meteorite. And so that is irrelevant to what Earth had. It's really a quantitative measure of what was lost from Mars over the last 4.3 billion years. And so one can argue about whether the Earth's number should be smaller originally or not than VSMO. That's a very valid argument. But what we can say is that the DOH ratio in this early Mars meteorite was, in fact, forget about VSMO, it was essentially 9 times the the nebular value of D to H. Okay, that's a better metric in my view, because we know Earth VSMO is enriched by a factor of 7 relative to nebular hydrogen. So I think we want to take the Earth out of the picture. Mars still lost an ocean in the last 4.3 billion years. It was on the size of the Arctic Ocean.
So something that comes up, bringing it back to the more broad topic of water worlds, is if that amount of water was delivered to Mars and this amount of water was delivered to Earth, are those small numbers compared to what we expect on water worlds, or is that a large amount? Sort of in the broader scope of planetary diversity, do we have a definition for water worlds? And I think that's a good question to start with. Is there any way to keep track of where it even came from? So, I think we've got about 5 minutes. Oh, no, 1 minute. So you can have that conversation over dinner.
Frame the question. Is a water world something that has no continents, or is it something that has 1 or 10% water by mass? I think we should decide that.
Well, I think you would be hard-pressed to have continents if you had 10 weight% water.
Well, right. But if it's only like 5 oceans, and you just submerge the Himalayas, is that now what
right.
the same
Yeah.
thing?
So defining a water world in terms of its behavior, not necessarily a number.
Yeah, so GCMs that use like surface oceans often call them aquaplanets. So maybe we could call water worlds the things that are mostly water by mass, then call the things that are covered in water aquaplanets. That could work.
Done. Thanks, Tad.
I'll stop using the term.
All right, thank you, everyone. Thank all the speakers again, and have a great evening. And